Hey everyone, and welcome back to The Explainer. Today, we're diving into a genuinely fascinating journey. We're going to start way zoomed out, looking at some major state-level climate funding, and then we're going to zoom all the way in to a highly specific and frankly mind-blowing carbon-negative technological breakthrough. But before we get to that breakthrough tech, just wrap your head around this number for a second. 400 million tons. That is the amount of CO2 equivalent emissions pumped into our atmosphere every single year globally from one very specific practice, flare gas burning. It's an absolutely massive environmental problem, but it immediately sets the incredibly high stakes for the solution we're unpacking today. Okay, let's dive into this. Here's our roadmap. We'll start with investing in climate innovations, move right into the off-grid charging need, check out mobile EV charging solutions, tackle the flare gas problem, explore carbon-negative EV charging, and finally, look at scaling sustainable infrastructure. Starting off with Section 1, investing in climate innovations and the financial push behind it. True lasting decarbonization really kicks off with serious governmental and financial momentum, right? It's about getting these concepts off a whiteboard and into the real world. We're seeing exactly that kind of momentum with a recent $3.9 million investment from the Healey-Driscoll administration in Massachusetts. This funding is flowing through the Mass CEC Critical Mass program. And what's absolutely vital to understand here is the program's specific focus. It's literally designed to help climate tech startups jump from their initial pilot demos directly into commercial deployment. It's all about getting viable projects operating at scale. So this critical mass funding is backing a pretty diverse spread of clean energy projects. We've got AirShield scoring $1 million for aerogel insulated windows, Luminous Robotics snagging nearly $1 million for autonomous solar site robots, and MBU with over $970,000 for a multi-family virtual power plant. But let's zoom in on that last one, Spark Charge. They were awarded $1 million specifically to deploy mobile off-grid DC fast charging hubs. This targeted investment in off-grid infrastructure is basically our pivot point for today's whole explainer. Moving on to Section 2, the off-grid charging needs and how we overcome these bottlenecks. So what's the actual hurdle innovators like Spark Charge are tackling? Well, it boils down to a fundamental lack of reliable, scalable electric grid access for commercial fleets. Think about it. Standard grid-tie charging is entirely reliant on our existing infrastructure. And honestly, upgrading the grid can be painfully slow. Plus, depending on where you live, that grid might still be heavily dependent on fossil fuels anyway. Off-grid mobile solutions, on the other hand, operate on a completely different logic. They offer rapid, immediate deployment, they're entirely independent of local grid bottlenecks, which makes them highly flexible and scalable for growing EV fleets. Which brings us to Section 3, mobile EV charging solutions, and the innovators making them happen. Different private sector companies are tackling this off-grid challenge with some pretty distinct engineering approaches. Take Spark Charge, which we just mentioned. They use battery energy storage systems, or BESS. It's super effective, but it typically requires the mobile unit to be towed by a completely separate vehicle. Now, compare that to L-Charge, a California-based provider. They've engineered a system using power takeoff, or PTO, engine integration. They've essentially achieved a market first here. They combined a 60-kilowatt DC fast charger directly into a functional fleet service truck bed. So they completely eliminated the need for extra towing or separate onboard batteries just for the charger. And this brilliantly illustrates L-Charge's approach for heavy-duty off-grid setups. They use these modular gas-powered generators that are engineered to only run when charging is actively taking place. This smart design drastically cuts down on idling emissions compared to your standard gas generator infrastructure that just sits there burning fuel all day long. All right, Section 4, the flare gas problem. An environmental challenge. Now, to fuel these off-grid generators, we actually have to circle back to that massive 400 million ton emission figure we started with. Flare gas burning is incredibly common during oil extraction. Basically, the waste gas that comes up with the oil is just burned right off at the wellhead. It's a severe environmental issue because this flaring releases immense amounts of methane, carbon dioxide, and black carbon directly into our atmosphere. It's quite literally just harmful pollution from a wasted byproduct. We'll enter Macaw Energies and their F2X technology. This is a real game changer and the critical solution we've been looking for. This tech actively captures that harmful wasted flare gas right at the source and converts it into what they call liquid flare, which is a usable, transportable form of liquefied natural gas. They are taking a severe pollutant and transforming the whole shebang into a highly deployable energy commodity.
which perfectly sets up Section 5, carbon-negative EV charging, a scientific breakthrough.
Get ready, because this is an absolute paradigm shift for how we think about fueling off-grid EV chargers. Let's break this down clearly, minus the jargon. You hear carbon neutral all the time, right? But this is carbon negative. That's a verified rating, meaning greenhouse gases are actively being removed from the atmosphere or directly avoided during the product's life cycle. Simply put, using this specific fuel is actually better for the atmosphere than just breaking even.
Negative 43 kilograms of CO2 equivalent per MMBTU. Let that sink in. That is the verified well-to-pump carbon intensity of liquid flare. It's a beautifully measurable, wildly impressive metric that shows exactly how much atmospheric emission is being actively avoided just by capturing that gas before it burns off at the well. So the crucial point is how these distinct technologies actually merge out in the real world. Down in Houston, L-Charge has deployed an off-grid charging station that specifically uses liquid flare to power an electric ride-sharing fleet. We are looking at a completely closed-loop system working today, capturing waste emissions at the source, turning them into a transportable fuel, and using that fuel to charge zero-emission vehicles completely independent of the power grid. Finally, Section 6, scaling sustainable infrastructure and looking at the big picture. So what does this highly localized breakthrough in Texas actually mean for global energy systems and future decarbonization? Well, it builds a complete sustainable ecosystem in 3 straightforward steps. Step 1, you capture the harmful flare gas right at the source, preventing that methane and black carbon release. Step 2, you convert that waste into transportable liquid flare. And step 3, you use that portable fuel to power off-grid EV fleets wherever they're needed. It's a perfect demonstration of how initial investments in off-grid infrastructure directly enable these massive waste-to-energy solutions. And honestly, the broader implications of liquid flare are absolutely staggering. This goes way beyond just electric vehicles. Because it's such a versatile, transportable commodity, we're looking at global scalability. We can use this stuff to power data centers, which, as we know, have massive growing energy demands. We can use it for heavy industrial power generation. We are simultaneously slashing emissions, eliminating a major environmental hazard, and creating very real cost savings for massive industries. As we wrap up this explainer, I want to leave you with something to chew on. If we can successfully capture millions of tons of harmful flare gas and turn it into carbon-negative fuel to charge our electric vehicles, what other industrial waste streams could be productively repurposed to power our clean energy future? The potential for closed-loop sustainability is definitely out there, just waiting to be engineered. Thanks so much for joining me, and keep learning.